Hey students, time for another video here, or video solution. This is our interference stuff from optics in chapter 37, number 63. It looks like the textbook has it in magenta in color, so this should be a bit of a challenging one. And it starts off and says, refer to question 37.8. So I went ahead and printed that here first. And, well, let me read the first sentence, and then we'll come back and look at this before we can go on to the whole question here. It says, but the figure 37.8 shows an unbroken soap film in a circular frame. The film thickness increases from the top to the bottom, slowly at first, and then rapidly. So they're kind of showing a kind of a face-on look here. But if I were to do a cross-section, so looking from the side, this might look something like this. It's getting real thin at the top, and it kind of spreads out near the bottom. And so this would be kind of a side view here, looking at it. Watch, maybe I should keep reading here. Let's see, the increases at the top, the bottom, and then rapidly. As a simpler model, consider a film that consists within the rectangular frame, and the frame is held vertical. So, all right, let me pause right there and just kind of finish this here. Let's try to get a conceptual understanding of this before we go on to the problem here. But it says, as a soap bubble, it evaporates. It appears to be a black immediately before it breaks, as the top of the circle film shows in this figure. And so notice it's black up here. Can you explain this phenomenon in terms of the phase change that occurs upon reflection from the two surfaces? Yes, we can. What's going to happen here is the light's going to go in, and I'll draw it near the top since that's the question. And it's going to reflect off of the front surface. If it's really, really thin, we'll say that it doesn't travel but a microscopic distance. And so it really doesn't have, I'll just say, much of a wavelength distance. Let's say 1/100th of a wavelength. And then that reflects off the backside. And as those two beams come back to an observer, and so somebody who is observing this reflecting light, what they're going to see then is an actual destructive interference, because the first beam is going from an index of 1, air, into the soap bubble, which is mostly water, so we'll call it an index of 1.33. And so it undergoes a phase change. And the other one, which is bouncing from the water into the backside, which is air, does not. And that means these two beams coming back are out of phase, because one does a phase shift, which is equivalent to a half wavelength, and the other one does not. And if we're so thin, it really doesn't matter what the wavelength is, it will cancel. And so the whole rainbow of white light that is hitting it, every single color would cancel itself out and look black, would have destructive interference. And that's what you're seeing right here. And as you go down, you can then begin to see some bands of colors. And I think that's where this starts to come into play. But at least I think we have a conceptual understanding of what's going on in this problem by coming back to this question, number 8 here, and getting an idea of the phase change. So keeping that in mind, let's go back to this problem here. It says we're going to consider a simpler model. So as a simpler model, consider a soap bubble film, and then there's the index, contained within a rectangular wire frame. The frame is held vertical so that the film drains downward and forms a wedge of flat faces. And so kind of unlike the question 8 here where it says the soap bubble evaporates, it appears black immediately before the top. Phenomenon in terms of the phase change. I thought it said it got thicker. That was up here. So the film increases its thickness from top to bottom and then slowly at first. And so that's why I gave it kind of a little bit of a swooping pattern. But to answer number 63, they say, let's make it a little bit easier. By number 1, not worrying about a circular frame, okay? And then number 2, it's rectangular, and I'm going to do a side view again. And so what I'll have is this wedge shape with flat faces. And of course, that's going to make the math a lot easier. That's why they're saying, let's, consider a simpler model. Maybe not realistic, but at least somewhat close to realistic. And it has this nice wedge. And so this wedge has some kind of wedge angle theta that fans out. And I think that's going to be the question. Look at, question C. What is this wedge angle of the film? Okay. Now, all of these interference patterns, and so really everything in chapter 37, hopefully you're kind of seeing the same idea. And I'll just kind of draw some light coming in to the front. Remember, we're doing a side view. So the light comes in, and as we just talked about, one beam bounces off and has a phase change, and the other one goes through, bouncing off the backside, and does not have a phase change. The two then overlap as they interfere with each other and come to our observer. And so there's going to be some either fully constructive or fully destructive or something in between. And as a quick reminder here, if we call this place where the light travels thickness T, I like to say the second one travels an extra distance of 2T. And I always like to begin by saying if 2T is an integer number of wavelengths, and I should say wavelengths in the material itself, then you will get constructive interference. And if 2T is an integer and a half, you'll get your destructive interference. And so that's what would happen if we ignore any kind of phase shift. And so I always like to do that first and then start to ask, well, are there any? And of course, as we mentioned earlier, the answer is yes to that. And so it is phase shifting on this first one, but not the second one. And so what you might have considered constructive interference now becomes destructive, because these two extra, or the extra path length, this bottom one, 2T, might have been one wavelength or two wavelength, and you might have thought, hey, they come up in phase. But because the first one changes its phase, they actually end up in destructive interference. With fingers, I guess I like to say this. Two beams come in together. The one that travels through the medium, maybe two wavelengths like this, and then they come out in phase. You're like, yeah, okay. But because the first one then changes its phase on reflection, they're destructive interference. And so this is the equation we would look at for a minimum of amount of light reflected. And this is the equation we want for maximum light being reflected. And that's what we have here. We are having maximum light. And let me keep reading. The frame is held vertical so that the film drains downward and forms a wedge of with flat faces. The thickness of the film at the top is essentially 0. The film is viewed in reflected white light with near normal incidence. Okay, so, and I'll pause there for a second, but this is our description where the light comes in and it's white light, hits here, bounces off, and comes back. And so we're looking at reflected light. And anything that looks bright or stands out must be satisfying this equation. And so parts of this wedge will have the appropriate thickness with the appropriate wavelength to look bright. And so if we, well, let me go to a second page here. But page 2, then, if you look at our options, we have this 2t. Actually, just let me do the t by itself. We have this m plus a half, and then we have lambda over 2n, where remember, m can be a 0 or a 1 or a 2 or a 3, ... And so what we would consider the first case where we would get some brightness is we'd put in a 0. And so this would make a lambda over 4n. The next thickness that would give us an appropriate brightness is when m equals 1. And so 1 plus a half is 3 over 2. And then that makes 3 over 4, lambda over n. The next appropriate thickness, m would equal a 2. 2 plus a half is 2.5. That's like 5 over 2. And so that makes 5 over 4. Okay. Lambda over n. And then, of course, all kinds of other thicknesses. And that's for a particular wavelength. And because this problem is sending in white light, we can say we have any appropriate wavelength. And so we would look at this, and as you can kind of see, you would get, the shortest wavelength would correspond to the shortest thickness. So there's kind of a blue or a violet. And then the next longer wavelength, maybe I'll just, kind of hard to see in this picture, but, if we do our Roy G. Biv again, there should be a little band of a green, and then a yellow, and then an orange, and then a red, and then the blues and violets again. And so that pattern would continue as we go to each order for all of the wavelengths. Now, for us, in this one, they're saying the first violet, and they give us a wavelength for the particular violet, interference band is observed 3 centimeters from the top of the wedge. Okay, so the first one would correspond to this thickness. So if I put in the 420 nanometers for the wavelength of light, and I divide it by a 4 and a 1.33 for the index, grab my calculator here, I got the 420, I divide by 4 and also by 1.33. We're looking at 78.9 nanometers for the thickness of that violet light. And let's see, what's the first question here? Now they tell us it's 3 centimeters down, but watch this. A, locate the first red one. Okay, and so the red one has a thicker wavelength, obviously, or excuse me, a bigger wavelength, which would mean a thicker place. So actually, let me calculate that thickness. So the thickness for the red, and this was thickness for the violet, okay, would be then the 680 divided by the 4 divided by the 1.33. And so we're looking at a thickness of 127.8 nanometers. So this is where the red thickness is. In fact, maybe it's worth drawing this wedge again. And I'll kind of say, okay, so right here would be the thickness of the violet one. A little further down would be the thickness of the red one. And this, they said, is 3 centimeters down. So clearly the red one must be a little bit further. But you can kind of see the similar triangle setup. If I look at the violet one and I do its height over its base, and then compare that to the red one, which is its height over its base. And so looking at kind of this triangle, I can do a quick bit of geometry with similar triangles. That is, for the violet triangle, and that has to be equal then to the pattern for the red triangle, I could take the height of the violet triangle, which is 3 centimeters, over its base, which was the 87.9 nanometers. I won't even bother to do a unit conversion. I'll leave them as weird units here. Because if I do that for the red, I could say the red is down a distance x in centimeters, so this is x, when it has a thickness of 127.8 nanometers. Solve for x. And so the nanometers go away, and I'm going to have a left with the units of centimeters. So I'll take that first answer, 127, and divide it by the thickness of the violet. And so I get a factor of 1.62. And so times the 3, and we should be looking at about 4.86 centimeters down. Again, about 60% further down than the 3 centimeters. Okay. So there's A, locate the first red interference band. B, determine the film thickness at the position of the violet and the red band. Well, I guess I've already done that. That was kind of what got me started here using the interference. So this would be the thickness of at the violet band, and this would be the thickness at the first red band. And then it would, again, go violet to red and violet to red. And like I said, here's the picture, violet to red, violet to red, violet to red, as it has different sets of thicknesses. All right, so I guess this is the answer to B, and this was the answer to A. Now C, what does C have? C says, what is the wedge angle? All right, and so maybe coming back to this picture, and of course, it doesn't matter which one you look at. You can look at the triangle for the violet or the triangle for the red, since they have the same wedge angle. I'll go ahead and do the violet one. And if I call this whole angle here theta for the wedge angle, and I just make a little triangle. Let's see if I can make it kind of stand out, because I'm going to do half the angle theta. I'm going to come on down here and make a right triangle out of this wedge. And so in here is really a theta over 2. But mathematically then I could do this. Mathematically I could say, all right, let's take the tangent of theta over 2. Okay. Checking my lighting here. Something didn't seem quite right. Oh, there we go. Let's straighten that out. Okay. Tangent. So if I do a tangent of theta over 2 and go to the violet, it would be half of the thickness here of the violet. So I'll go 1/2 of the 78.9 nanometers, divided by this height, which is 3 centimeters. Now, here I'll definitely need to watch my units and make sure they cancel off, because I need a ratio with no units, and so I need these to be either nanometer over nanometer, or centimeter over centimeter, or meter over meter, and I think that's what I'll do. I'll just take the 1/2 times the 87.9 and get a 39.45 nanometers. And in this bottom, I'll do 0.03 meters, so my meters cancel off. So if I take this answer and multiply it by a nano, oh, little typo there. Let me try that again. 39.45 nanometers. And then divide that by the 0.03 meters for the 3 centimeters. I get this ratio. And I'm in radians. Let's just switch this over to degrees. There we go. And so now if I do the arc tangent of that, I get a theta over 2 of 7.53 times 10 to the minus 5, and we are in degrees. And finally, to get the wedge angle, I would double it. And so 1.51 times 10 to the negative 4 degrees. So not much of a wedge angle, but then again, I guess that's to be expected. When I played with soap bubble films, you don't actually see much of the wedge. All right. Hope that helped, and thanks for asking questions, and keep them coming. Bye.